theorists in the world of neuroscience will tell us that what neurons and neural networks are really good at is picking up on the structure of the world around us and changing their responses so they're basically compressing their input. So, when you're seeing stuff,
Right.
you're seeing my face right now, you're not getting a bunch of random inputs. There's structure in this image, and your visual cortex is really, really fine-tuned to respond to that structure. And so we think that the organoids might be doing something similar, because that's not just what neurons do.
Dr. Daniel Toker, thank you for coming on the Augmented Life.
Thank you for having me.
I am particularly excited to talk about the intersection of neurobiology, computation, and a little bit of information theory. I see references to things I think of as Shannon information theory in your findings about consciousness. And I think a lot of people who are listening to us have some model of at least how neural networks work mathematically, because we've been building artificial ones. But when looking at your research, I've always wanted to ask this question: if you've got a model of how a neural network works and how information is structured, there's no obvious correlate in the math to brain waves. But I think all of us have heard that brain waves are a thing, and you can read them. What what are they arising out of? Like to tell us what's causing brain waves.
Yeah, that's a fantastic question. So you're right that right now, all of our computing artificial neural networks, none of them have anything at all like brainwaves. And that might be partially because at the level of neuroscience, we're not entirely sure what brainwaves are doing computationally. There are a lot of ideas out there, um, and many different camps. But we do know that you need a lot of neurons all acting in synchrony to create brainwaves. You probably also need different brain regions communicating in various ways. So we know when you look at brainwaves, there are a whole bunch of frequencies. You have all these oscillating waves of electric activity happening at once, and the origins of different frequencies of activity might be through interactions with different brain networks. So, for example, one of the most dominant rhythms that we see in the brain is the alpha wave. I think a lot of people have heard about it. It's most prominent in the back of the head or your visual cortex, especially when your eyes are closed. It's this 8 to 12 hertz wave, and we think that that's happening through interactions between a part of the brain called the cortex and a part of the brain called the thalamus. You have other waves called beta waves, which might be driven in part by another subcortical structure called the basal ganglia, but we still don't know computationally what they're doing, but there are a lot of ideas out there.
Right. Now, I think the thalamus is implicated in the question of what consciousness is. There seems to be some sort of network effect with the thalamus as its core. What have you found there?
Definitely. So the thalamus has sometimes been called the major relay station of the brain, which is probably oversimplified, but still a helpful way to think about it. So, you're looking at me right now, you're getting data from your eyes. That data is first being sent through your optic nerve into your thalamus, and then from your thalamus to your visual cortex. Same thing with auditory information, tactile information. Basically, all of your senses except for smell are going through your thalamus first. Your arousal system is also going through your thalamus first. So you have this part of your brainstem, which we sometimes call the reticular activating system. And this is basically what's keeping you awake or not awake. And that also is projecting from the brainstem to the thalamus, and then from the thalamus to the rest of the cortex.
Mhm.
And the cortex also sends feedback to the thalamus at every stage of processing. So it's probably not surprising that it's so important for consciousness, because all of these networks involved in sensory perception and in keeping you awake, so awareness and arousal, those are all going through the thalamus. And so if you completely knock out the thalamus, you will be in a coma or a vegetative state. But there's also a lot of research on how, for example, communication between the cortex and thalamus, how that's involved in consciousness, which I'm happy to dive into more.
Yeah, well, it seems to me like you've been pushing us forward into the edge of what's known, um, because just from first principles, based on the description you just gave, we can imagine that some sort of synchronicity is a requirement of consciousness, and so we can look for some signatures of that and go, okay, that's going to be our indicator of consciousness versus unconsciousness. But the reality is not so simple. It's not just a matter of indicators of this connectivity. You actually found by looking at study subjects with unusual brains, you could isolate some particular indicators measurable in an EEG that seem indicative of the conscious state versus the unconscious state, and that's where entropy, that's where information theory came up. Can you help our listeners, catch our listeners up? How did you find this?
Yeah, so maybe let's take a few steps back. Um, Traditionally, one of the um, most accepted correlates of someone being unconscious is the emergence of slow waves in the cortex or delta
Mhm.
waves. So those might be there always, but the volume gets turned up. So their amplitude is going up in various states of unconsciousness, like deep sleep, anesthesia, coma, generalized seizures.
Hmm.
But there are some states, as you mentioned, that sort of don't fit into the simplified picture. So, my colleagues and I have looked at the brainwaves of patients with a number of genetic mutations that affects their large scale brain activity. So, one of these is Angelman syndrome or Angelman syndrome. So, this is associated with intellectual disability, but from the perspective of consciousness, the reason this is interesting is because they have these huge delta waves all the time, even when they're awake. And so if we were to think, okay, if you have delta waves, therefore you can't be conscious, then that's clearly not true for these patients because they have delta waves all the time, even when they're awake and talking. And so what my colleagues and I did is we looked at what is changing in their brains when they're in deep sleep. So the delta waves, they're still there. They're still very strong when they're in deep sleep. But is there maybe a more fundamental thing that's changing that can track the loss of consciousness? And maybe this is a bit of a spoiler, but the answer is complexity or entropy. And we can dive more into what that actually means. But we also looked at the brainwaves of patients who have Dupe 15q syndrome. And in a way, this is almost the opposite of Angelman syndrome, where their brains look awake even when they're in deep sleep. So they don't ever really get these big delta waves. Their brainwaves are always sort of small and fast, which is typically what we see when someone is awake and conscious. And for them too, you see a loss of entropy or complexity in their brainwaves when they're in deep sleep or unconscious, which means that this previous picture that we had of delta waves means unconsciousness is really only true for neurotypical brains. But this loss of entropy or complexity seems to be a universal correlate of unconsciousness. And we see it in anesthesia, we see it in coma, we see it in seizures, we see it in vegetative states, we see it in minimally conscious states, we see it in deep sleep, and we see it across species.
Wow. Now, how do you measure, how do you come up with with a measurement of complexity that you can apply across these subjects?
So there are many different flavors of complexity or entropy. And I think maybe before we get into the mathematical specificity, um, an example I often like to give for why entropy is relevant for understanding how much information a system can carry is imagine if I'm talking to you and all I could say is the word cat over and over again. I can't change the intervals between every instance of this word. I can't change how I'm saying it. So basically, all I'm saying is cat, 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 cat. That is a very predictable signal. So it's going to be low entropy and therefore cannot carry any information. The reason that human language can carry so much information is because it's unpredictable, therefore it's high entropy. So mathematically, entropy basically sets a bound on how much information a signal can carry.
Mhm.
So when we see entropy going down or signal entropy going down in the brainwaves of people who are unconscious, that means that their brainwaves are just mathematically not as able to carry information. Now, when we say things like complexity is going down, these things are very related. So, a lot of these complexity measures are the basically measuring how compressible a signal is. So if I were to take a recording of your brainwaves and I would try to make a compressed file, it's looking at how big that compressed file is. And mathematically, that's also connected to entropy because entropy sets a bound on how compressible a signal is. So it's really another way of saying the same thing of when you're unconscious, your brainwaves are carrying less information.
Yes. All right. And so you can actually apply some of those mathematical techniques, drawn not least from signal processing, say how compressible is this?
Yep.
And low compressibility means high entropy, which is weirdly correlated with actually being awake.
Exactly. Yep.
Wow. The and I think you also discovered fascinatingly that the opposite seemed to obtain under psychedelics. So um like I'll just try using the personal pronoun here. It seems like the evident complexity of my brainwaves goes down when I fall asleep and goes up if I take, a heroic dose of LSD or something.
Yeah. Yeah. So I should clarify that I'm not the first person to show this. So um, psychedelics are really fascinating because the psychedelic state is the only state that we know of that will increase the complexity or the entropy of your brainwaves relative to the normal waking state. I was not the first to show this. I have replicated that in my own data. Um, my research was more about why. How is the complexity or the entropy or the ability to process information, why is that going up in psychedelic states versus going down in all these different states of unconsciousness? So that's where my work in chaos theory comes in, which I'm happy to dive into.
I would love to get into that. I'll try to set the stage in the following way, just because of my own background in chaos theory. A lot of the work of chaos theory arose at the same time as computers were invented, because this is a discovery that requires, I think, a high density of computation. One of the leading lights, Lorentz, actually worked in weather prediction, and and the story goes that they almost accidentally discovered the Lorentz attractor, um, where it at one level, and here's the Michael Tiffany kind of quirky way of describing this. At one level of dimensionality, if you look at the output of the equations that underlie the Lorentz attractor as like a table of numbers, it looks totally chaotic. It just looks like a series of random numbers. However, if you give every one of the variables in those equations its own dimension and phase space, you get literally a beautiful picture called the Lorentz attractor. And one of the reasons why this picture is so beautiful is that it's bounded. So in phase space, you see a shape, whereas in a table, you see just random numbers. The shape has boundaries that every single number that'll ever be generated by the Lorentz equation fits in the bounds of what could be drawn as a very beautiful picture. Um, and the this entire field of chaos theory is something of an exploration of why that boundedness exists, what characterizes the dynamical systems that lead to those properties versus things that just oscillate or contract to nothing or expand to infinity. And it's certainly not obvious how this math relates to consciousness. So build us that bridge, please.
Yeah, happy to. So, um, as you're sort of hinting at, one of the hallmarks of a chaotic system is that it's not random. It's following these rules. So, as you said, if you look at the phase space, it's sort of following an orbit.
Right.
But if you slightly perturb the system, it'll still follow the general shape of the orbit, but the exact orbit will be very, very different. And so Lorentz called this the butterfly effect. Essentially, in a chaotic system, something as small as the flapping of a butterfly's wings can cause a tornado on the other side of the world. Now, mathematically, we can quantify how chaotic a system is. And so there's this mathematical number that sounds daunting, but it's not. It's called the largest Lyapunov exponent. And basically, all that means is how quickly do similar trajectories in phase space diverge. And so, let's say we were thinking about like a super stable orbit, you know,
Mhm.
like if you think about a well, I don't know if planets are periodic or not, but basically, imagine a planet that's orbiting super stably around its star. If it were stable, you could push that planet a little bit, and then it would just return to the exact same orbit as it was going before. So in this case, it would have a largest Lyapunov exponent that's negative because it's just going back to the same trajectory. If this exponent is positive, that means as you perturb it, it's going to diverge from its original orbit. And the exponent basically measures how quickly it's going to diverge from the orbit that it was on before. Now, since the early 90s, a lot of computer scientists have made this observation that when systems have this Lyapunov exponent near zero, something weird happens where systems can process a lot of information. And I should say that for as far as I know, mathematicians still don't really understand why this is the case.
Right.
It's and maybe it's because, chaotic nonlinear systems are just really hard to get a mathematical grip on, but this has been shown in a lot of different systems. Um, it's also been shown in deep neural networks. So there's this finding from, I think, 2016 in this paper called Deep Information Propagation, which showed that as deep neural networks, the sorts of networks that we use for AI, as their dynamics approach this, what we call the edge of chaos. So that means the system is neither chaotic nor is it stable. It's hovering right at that transition point. So as it approaches that transition point, information can pass through more and more and more and more layers of the deep neural network. And so, I was reading that literature showing that things like entropy and complexity all seem to go up into this critical point. And I was thinking, what if this can explain what we're seeing with changes in the entropy or complexity of the brain's activity when we're conscious or unconscious? So, other people had flirted with this idea before, but hadn't really expressed it in the mathematically precise terms of chaos theory. And so, if this picture is true, then we would expect the brain's activity should have a largest Lyapunov exponent close to zero when we're awake and conscious, and should have to become, positive or negative when we're unconscious. Uh, which might drive sort of the loss of entropy or complexity in these different unconscious states. And that does seem to be true. That's what we showed in coma, in generalized seizures. Those are the seizures that make you lose consciousness, and also in anesthesia. And what's interesting is that it looks like psychedelics tune the brain's activity closer to that edge of chaos, that largest Lyapunov exponent of zero, where more information can flow through a system.
That's fantastic. Wow. I so is it fair to say that at when we're characterizing systems in this way and we're thinking about the edge of chaos, we're specifically drawing a distinction between high entropy measures that are nonetheless a part of a complex adaptive system. So they seem to somehow have information processing or handling capabilities versus high noise that's just it's uncompressible because it's like literally random.
Yeah.
So they look superficially similar.
Yeah, it's a good point, and it's difficult experimentally to tease these apart. So, as you're saying, if you have a truly just completely random system, that's going to be the most complex high entropy system by definition. Um, that we're getting into a little bit of the mathematical subtlety here, so I should give a caveat that in our work we were finding that this high complexity at the edge of chaos is only true if the system is getting these noisy inputs. So if you have a completely deterministic system, then the more chaotic it gets, the more complex or high entropy it's going to get. When it's getting these complex inputs, for whatever reason, and again, we don't fully understand why, but we've seen this in multiple systems, including in simulations of the brain,
Mhm.
that its entropy or complexity is going to be highest at the edge of chaos. And that could be because when it's at the edge of chaos, it's most able to represent complex inputs, but I guess that's speculation. We don't really know mathematically why.
Right. Oh, this reminded me of another, I think, key insight from the dawn of chaos theory, which is that these complex systems that have this property of high perturbability can actually be characterized by relatively simple equations. Like the Lorentz equations are very simple. And prior to this discovery, it was thought that of course you could build some, you know, highly complex outputs from highly complex inputs. But the surprising fact is that relatively simple equations could also produce this high rate of perturbability. And that leads me to my next line of inquiry. You've been trying to think about how to simplify like a brain system, right? A model of a brain system in such a way that it still shows this high complexity, but is itself a almost simple unit of modeling with your work on organoids. Tell us about this.
Yeah, so I've actually been trying to. There are two branches of this work, and so one is actually just creating simulations of the brain. And when we simulate brain waves with this large scale activity, we're not using equations for every single neuron. We have an equation for, what is the average level of activity for, some chunk of brain tissue, and what do the outgoing electric fields from that chunk of brain look like. We can still create very complex dynamics using relatively simple equations. And so part of my research has been on trying to make these large scale brain simulations that, on the one hand, are relatively simple, but on the other hand, can capture some of the complex patterns of activity that we see when the brain is conscious and awake.
Uh-huh.
We also have these organoid models, as you were hinting at, and these are they're they're simple in a way, but also quite complex in a way. So these are grown from stem cells, and those stem cells are they're induced pluripotent stem cells. So basically, we take skin cells from a patient, we turn those skin cells into stem cells. We then aggregate those stem cells together and give them factors that turn them into neurons, and we turn them into the types of neurons that you would see in the cortex, for example, which is one brain region, or the hippocampus, which is another brain region, or the ganglionic eminence, which is another brain region. And we can then combine these in different ways. And so we can have one, what we call assembloid, which is a fusion of a cortical organoid and a ganglionic eminence organoid. And this is going to be far, far simpler than the circuitry that we have in the actual brain. But at the same time, it's going to be a lot more complex than just looking at single cells in a dish. It's complex enough to start generating brainwaves.
Wow. Wow. All right. So it's complex enough to start generating brainwaves, and it's drawn from actual people. Like I could have a tiny little brain circuit model from my own cells.
Yep.
This is astonishing. And I love how at a relatively small scale, it's generating brainwaves. That blows my mind.
Yeah, I mean, they seem to do. Yeah, the organoid field is pretty new, but there's also been research which is fascinating and maybe a little bit worrisome. This is not what we do. This is just what people out there in the world are doing, which is you might call it lab grown intelligence. So it's using organoids and showing that they can actually do computational tasks.
Ooh, ooh, all right. So we're probably not factoring primes.
No, no, no. So there were two papers on this. I think that the one that I'm personally more convinced by, just based on what I know about AI and also about organoids, basically treated organoids as these reservoir networks. So um, reservoir computing is a branch of machine learning where you it's typically used to predict a complex signal. So it's actually often used in, you can give a reservoir machine, they call it a chaotic signal, like the Lorentz attractor,
Mhm,
and you can use it to predict where it's going to go next. And the practical application is things like, predicting like stock market fluctuations, or, there's practical utility to it.
mhm.
But the strength of this form of machine learning is that you don't actually need to be tuning the network itself. You're just using it to I should rephrase that. So you're giving it an input, and then all you're doing is training the thing that's reading the outputs. Um, and so that's great because you don't need to know exactly how the organoid is representing information. And so
Yeah.
people fed signals into organoids. They read out the organoid's electrical activity, and they were able to um, use this to predict how signals will evolve. Now, what's really fascinating is that organoids got better at this with time without any explicit training. So again, the researchers are not giving any feedback to the organoids. The organoids are just getting these signals. The researchers are reading out the outputs, and they're doing their machine learning sort of offline on the outputs. But just by virtue of getting these signals inputted into the organoids, without any feedback or training, are getting better and better at parsing out these inputs and generating more unique responses to different unique inputs, which then improves the output of the organoid.
Oh, that really blows my mind. I mean, before you said this, if you had asked me, I think I would have said with high conviction that feedback loops are a requirement for learning.
I
Whoa.
mean, they're definitely involved in some form of learning, but I think this speaks to the magic, if you will, of biological neural networks. So, theorists in the world of neuroscience will tell us that what neurons and neural networks are really good at is picking up on the structure of the world around us
Right.
and changing their responses so they're basically compressing their input. So,
Yeah, that makes sense. Right.
when you're seeing stuff, you're seeing my face right now, you're not getting a bunch of random inputs. There's structure in this image, and your visual cortex is really, really fine-tuned to respond to that structure. And so we think that the organoids might be doing something similar because that's not just what neurons do.
Yeah, right. Like, certainly I find it compelling that at a high level, the brain seems to be doing some one, predictive processing, that two, seems to seek Bayesian error reduction, right? So maybe maybe the mechanism of that action is actually like really small. It's not a giant emergent property of like lots and lots of neurons. It's something
Yeah.
that's
Yeah, it could be both. It's probably both.
uh uh yeah, okay. Oh, that's wild. All right, so the where are you going next with these insights? Like, bring us to the edge of your research.
Oh gosh. So right now, um, what I'm working on primarily is thinking about concrete treatments for patients with disorders of consciousness, so things like coma, vegetative state. And there's been kind of two branches of this work. One is a bit more related to what we've been talking about, which is using these large scale brain simulations to generate models, realistic models of the brain when it's in a coma or vegetative state, and then looking at how can we perturb the brain to basically shift brain activity to look more awake and conscious. So that's one branch. The other branch, I've been giving anesthesia to organoids to see if we can use them as models of coma. Uh, so far, it looks like we can. And that could be a game changer in the future because that means we can use human brain tissue in a lab to look for new medications that could wake people up.
Oh, now, okay, when you're pursuing that, are you finding so given that you're growing these things out of stem cells drawn from real people, are you finding general principles, or are you finding how individual biology is different? So, like, am I going to react differently to an anesthesia than others, and is that an important dimension of this research?
So, both. Right now, it's just proof of principle. Just
Okay. Mhm.
can organoids even do this at all? Because no one's
Yeah.
tried that. In the future, certainly you can. So for example, we know that people with red hair typically require more anesthesia than people who don't have red hair, and we don't really understand why. So, in principle, in the future, you could grow an organoid from a brain organoid from someone who has red hair and maybe see at the circuit level what is maybe causing that. Um, which is one element. Yeah, so part of the promise of organoids is that they can be a platform for personalized medicine in the future. Right now, they're still in the developmental phase. There are already some people who are using them for personalized treatments, I think for cancer. But when it comes to personalized neurological treatments, we're still in the sort of proof of principle stage.
Yeah, understood. Okay. So, all right. While I think it would be interesting to make my own brain model, little organoid in a petri dish, and then feed it, 5-MeO DMT, just to see what happens. Um, Let me consider a different instrumentation challenge. Um, are are there ways in which I should perhaps instrument my like brainwave patterns now to capture me as a 44-year-old that would be useful to me as a 54-year-old? Like, are there longitudinal shifts?
Yeah, that is an interesting question. Um, there are subtle shifts in brainwaves with age. I'm not an expert on that, so I don't want to say anything that's incorrect. Uh, but I'm going to maybe sidestep the question with an interesting finding that's maybe relevant to your line of thinking here. Um, One way to shift your brainwaves now, which we know is going to be protective for your brain in the future, is meditation.
Ooh, okay,
So,
yes.
meditation is another way. We still don't know exactly what's happening in the brain when we meditate, but there's been a lot of research on these really fast oscillations called gamma waves. So that's stuff that's happening between, let's say, 30 to 80 cycles per second. So it seems that maybe their volume goes up when we are meditating, or maybe the synchrony of these waves across the brain is going up when we're meditating. But we also know that long term meditators can preserve critical aspects of brain function as they age. So we know that there's thinning of some parts of the cortex with age, particularly the prefrontal cortex, and that seems to be preserved in long-term meditators.
Ooh, ooh, is that like that's a line of instrumentation I would be really interested in. There are several subjective changes that I felt because of my meditation practice that I'm just left to, hypothesize about whether there are actual neurobiological correlates for, that subjective experience. I've I have a long time practice that led it felt like suddenly my experience of pain was different in that I I used to experience pain as this sort of single phenomenon, and then it seemed like all of a sudden I could distinguish 2 different things. There was like the signal of pain and the feeling of suffering from it, and I could just decide to do one and not the other. It wasn't like suppressing, like, I was still processing the pain. I was just, like, choosing not to.
Yeah, you can observe it and not be in it.
Yeah. Yeah, I wonder if there's a way that this th the I wonder if that's I wonder if there's a before and after, right? Like, if you could have seen something in my brain that, before and then after this shift.
Yeah. I mean, probably. There Yeah, I mean, if we stuck you in an fMRI or
Yeah.
MRI or,
Yeah.
longitudinally, there's certainly brain correlates of this
Right.
practice. I
Right.
actually I meditate myself at least 1 long session per week.
Uh-huh, nice. I'm only just now I wonder if some of these long-term neuroprotective effects come from altered states that I'm just playing around with now, like entering the jhanas does seem to be again, subjectively, it feels like an extraordinary increase in input. So I wonder if it's leading to the same kind of effects that you saw with, that increase in information carrying capacity coming from psychedelics. Yeah.
Maybe I think there actually has been work on this, but I don't remember the findings off the top of my head. So, yeah, I mean, there's certainly subjectively and in terms of long-term effects, some overlap between psychedelic, usage and meditation. Um, but I wonder how much overlap there is in the mechanisms by which you get there.
Yes. Right. Yeah, exactly. Right. Yeah. Yeah. Wow. Um, the well, you've opened my eyes in like several different dimensions of neurological research. If the same effect has been happening to those listening, tell us how they can find more of your work. How do they find you online?
Yeah, so I go by the brain scientist across social media platforms. So on Instagram, the_brain_scientist. You can also find me at thebrainscientist.com. I also have a new podcast myself called The Brain Scientist, where I interview other researchers in my world so I can give them a platform too.
Fabulous. Thanks for spending some time with me. This has been absolutely fascinating.
Yeah, likewise. Thank you for inviting me.